Hello learners, welcome to VLSI Simplified and welcome to our video Introduction to Verilog Basics of Hardware Description Language. So this is the true beginning of your Verilog learning journey where we start building the mindset of a digital designer. In this video, we are going to set the stage for everything that follows in our Verilog series. We'll be finally get clarified on what Verilog is, how it differs from normal programming languages, and why it's the go-to choice for describing hardware. So if you are someone who is just getting started with VLSI, or even if you are brushing up your basics, then you are in the right place. So let's see what you will learn for today. Your learning roadmap. So in this video, you will learn what Verilog is and why it's important in digital design. How Verilog overtook VHDL and became the industry standard, and HDL versus programming languages, and how Verilog supports both digital and analog mixed signal designs. So by the end, you will have a strong foundation to start coding in Verilog. Alright, this is VLSI Simplified, and let's get started and let's simplify.
Throw me like a Hellcat.
How are silicon chip designed? So let's start with a simple question. Have you ever wondered how microprocessors, GPUs, and memory chips, the brains of our electronic devices, are actually designed? So now you might think, do engineers use languages like C, Python, or Java to design these chips? We use those languages for building softwares, right? Yeah. So engineers use the programs to design hardware. But here's the twist. Those languages like C, Python, and Java are great for writing software that runs on hardware, but they can't describe the hardware itself. So the traditional programming languages can't describe the hardware behavior at the transistor or gate level. So they weren't made for it. So if not Python or Java, what do engineers use? Well, that's where hardware description languages or HDLs come into play, and that brings us to Verilog. So let's dive deeper into what exactly an HDL is and how it's different from regular programming language. So HDL is programming language. So at first glance, Verilog looks similar to programming languages like C or Python, but it's fundamentally different. So Verilog is a hardware description language, which means it's used to describe and design actual hardware and not for software. As you can see from the table, HDLs describe hardware structures and behavior while programming languages focus on solving problems. HDLs run in parallel, just like hardware, whereas programming codes run step by step. HDLs generate digital circuits while programming languages generates machine code. The HDLs deals with hardware related data types like wires and registers, but the programming languages deals with software related data types like integers, floats and arrays. And most importantly, HDLs work with simulation time, modeling delays and clock cycles for accurate behavior. This parallelism and hardware focus makes HDLs a totally different mindset compared to traditional programming. So chip design flow. So before a chip ever makes into your phone, computer or car, it goes through a long and detailed journey. And that journey is called ASIC design flow. So ASIC stands for application specific integrated circuit, and this flow is heart of how high performance chips like microprocessor, GPUs, memory units and even AI accelerators are created. Now, why is this design flow so important? Because building a chip is extremely expensive and time consuming. So you can't afford to make a mistake after manufacturing. That's why everything is designed, simulated, verified and validated thoroughly in a software before it's ever turned into silicon. So in short, the ASIC flow helps engineers design and test chips virtually to make sure they behave exactly as intended long before anything is physically fabricated. Now that we know why we need a proper design flow before manufacturing, let's take a look at phases of chip design, which are broadly divided into two main parts. One is front end and back end design. So, front end design, this is all about defining the functionality of the chip. We start with specifications where we define what the chip should do, its performance goals, power limits, and features. Then comes to architecture design, where we plan how the chip will function, what modules it should have, how they interact, and how data flows between them. Once that's done, we write the actual code using RTL design, typically in Verilog or VHDL. So this code represents the logic of circuit. So after writing the code, we verify its correctness through RTL verification using test benches and simulations. Once we verify, the design is taken through synthesis, which converts the high-level RTL code into the gate-level netlist made up of logic gates. So coming to backend, now we move from logic to physical layout of the chip. So we start with the DFT, designed for testability, to insert test structures that help detect any defects after manufacturing. Then we move on to floor planning, where we define the layout and placement of major blocks on the chip. After that, placement and CTS, clock tree synthesis, which ensures all gates are properly placed and clock signals are balanced. In routing phase, we connect everything using multiple layers of metal wiring. Once all that is completed, we go through sign-off, which is the final round of checks before fabrication. Finally, the design is sent for fabrication, followed by packaging and testing, where chips are cut from the wafers, packaged, and tested before they go into the market. And that wraps up the big picture view of chip design and the role of HDLs. So you have seen how Verilog fits into the design flow and why it's such a critical tool in modern VLSI design. But we haven't answered the main question, that is, what is Verilog? Where did it come from and why is it so widely used? In the next video, we'll be diving into Verilog itself, exploring its history, advantages, and how it became the go-to language for chip designers. So stick around, the real fun begins when we start writing Verilog. That's it for today. If this video helped you, give it a thumbs up, share it with your VLSI buddies. Subscribe to our channel so you don't miss any upcoming videos. See you in the next video. Bye.